some examples for the assignment, and we at the end just briefly looked at that how this Fourier transform is useful in the analysis of a signal. So today we'll watch one video as well, and we'll see what is the physical significance of this. Right, so moving on to, now we will just combine both the Fourier cosine transform and Fourier sine transform. I'll just combine these two, and we will obtain the general expression for the Fourier transform. Okay. So if we write down the expression for the Fourier integral, then it is something like integral from 0 to infinity. You have a cos of x w plus b sine x w integral with respect to w, where your a is given by 1 over pi integral from minus infinity to infinity into f of v cos wv dv, and b is 1 over pi integral from minus infinity to infinity f of v sine w v dv. So that's the Fourier integral, which includes both the cosine and sine integrals. Now what we want to do is to obtain the Fourier transform, which would combine both of these. So it is simply just plugging in the values of this a and b into this equation. So we get the double integral. So you get double integral from 0 to infinity, and both these integrals, I'll just write it in a combined way. So integral from minus infinity to infinity, you have so f of v is common for both the functions. So I'll just write it outside, f of v into cos wv to cos x w. So this one, okay, plus sine wv to sine wx, and this integral is with respect to dv, okay, and the whole integral is with respect to w. So I have just simply substituted these values of a and b in this equation. So if you just simply combine these two, then this is going to be equal to, so this is simply a formula for cos alpha minus beta. Okay, so this is cos alpha cos beta plus sine alpha sine beta. So this should give you integral from 0 to infinity, integral from minus infinity to infinity, f of v into cos of, so I will just write down in a like I will take it this as a wx minus wv. Okay, it will be same because it's a cos function, it's an even function. So if you write wv minus wx or wx minus wv, both will be same. So that's the integral with respect to dv, and this is with respect to w. Okay, and now if you see that this whole function, it's an even function. So this is an even function for w. Okay, and if you see the whole integral, okay, ये जो पूरा integral है, so that is with respect to w. So for w, this whole integral is an even function. Okay, this is an even function. So for that, what I can write is, अच्छा, by the way, forgot to include this factor 1 over pi. है ना, ये वाला जो factor है, so that I should include. So this factor of 1 over pi, I'll just plug in here. So because now this is an even function, what I can write is that this will be the this whole integral is 1/2 times the integral of 0 to infinity. And so let me just write down first. So this is going to be 0 to infinity integral 0 to infinity f of v cos of wx minus wv dv dw. ठीक है. So
हेलो सर 2 by pi आएगा ना फैक्टर
2 by no, see, because what we do is we write down, if you have, just write down somewhere here. So if you have an even function which is minus infinity to plus infinity f of x dx, so what do you write? This is as a 2 times 0 to infinity. ठीक है. F of x dx. So what I'm writing, acha, sorry, it's my mistake. What I need to do here is that this integral, we are talking about this integral, है ना? So this should be, let me just erase this. So this should be minus infinity. Okay, and this is minus infinity to plus infinity. So what I was trying to say was that for this integral, for this integral, so because this is minus infinity to plus infinity is 2 times 0 to infinity fx dx, है ना? So this is 0 to infinity, तो ये वाला जो इंटीग्रल है, this one 0 to infinity, 0 to infinity, so we are writing it half times minus infinity to plus infinity. ठीक है? तो इसको मतलब इसके लिए we are writing, because this whole function is even function for w. So for this integral, we are writing it as minus infinity to infinity half times. So if you go back from here to here, तो ये, because this is an even function, तो 2 times हो जाएगा ना, 2 times 0 to infinity. So you will get this back. Okay, so 1 over 2 pi minus infinity to infinity. Now both the integrals are having the same limits. Okay, this is for cos. Now for sine function, we can write down that if you do the similar term for the sine, then that is going to be equal to 0. So what I mean to say is that if you have 1 over 2 pi (1 over 2 pi integral minus infinity to infinity), and if you have the same term for the sine, f of v sine of wx minus wv dv to dw, so this should be equal to 0, because this whole term which is an odd function for w, so this integral is going to be equal to 0. ठीक है? So what I can do is that I can add this whole function over here, plus यहाँ पे करके this whole function I can add up over here, because this is equal to 0. ठीक है? And then I can simply just utilize the Euler's formula. So Euler's formula जो है मतलब e raised to I theta cos theta plus I sin theta, and if I write down this expression for the e to the power I into wx minus wv, so that is going to be equal to cos of wx minus wv plus I sine of wx minus wv. All right, so if I want to combine both of these two, so I need this function also over here, f of v. So I'll just multiply it over here, f of v to f of v, both the side यहाँ पे भी हो जाएगा f of v. So when you write down this whole expression together, so you will have this f of v multiplied by this function cos wx minus wv plus I times this whole integral you will have, or I mean you can combine both the integrals together. Okay, so in that way one can write down the expression. So this is the expression for the f of x. So f of x equal to 1 over 2 pi integral from minus infinity to plus infinity, our first integral, and you have the second integral. Now it will be combined on the with the exponential power. So you will have minus infinity to plus infinity f of v into e to the power I wx minus wv. Now integration is going to be with respect to dv dw. Okay, so now this whole function is in the exponential form, and if I split up this whole function into two parts, 1 over under root 2 pi integral from minus infinity to infinity, and then you will have one other integral inside, 1 over under root 2 pi. So I'm just splitting it into two, integral from minus infinity to infinity into f of v with e to the power minus I w v. So I'm taking v as an integration parameter, so dv and bracket over, and what is that you are left with is the e to the power I wx, e to the power I wx, that is going to be with respect to dw. Okay, so this whole integral, this is called complex Fourier transform. And so this whole function is the function of, so if you integrate this, because it is integration with respect to v, so finally जो भी integral आपको मिलेगा, the value that it will be in the form of w. So that is a function of w, and that is called the Fourier transform of the given function f of x in the form of w, I mean in the function of w. So you will simply just write down this as an expression. So I'll just write down over here f of f hat as a function of w is equal to 1 over under root of 2 pi minus infinity to plus infinity. Now I will just change the parameter from v to x. So I'll just write the parameter from v to x, ये वाला जो parameter है. Now because we are finding the Fourier transform for the function f of x, so this is going to be equal to e to the power minus x into f of e to the power f of x into e to the power minus I wx dx. Okay, so whole integration is with respect to x, and it will give you the integral in the form of w as a function of w. So this is going to be the Fourier transform for the function f of x. So if you have any function f of x, and if you want to find the Fourier transform, then you simply multiply it by the e to the power minus I wx, and you integrate it from minus infinity to infinity with respect to x. So that should give you the Fourier transform for the function f of x. And the way we have done this previously, if you want to get back your function f of x, then you take the inverse Fourier transform of this. So that means f of x equal to the integral from minus infinity to plus infinity minus infinity to 1 over the root 2 pi, and you will have simply your Fourier as a function of w and e raised to minus I wx dw. Okay, so that will be the inverse Fourier transform. So simply for the given function, you just multiply it by an exponent by e raised to power minus I wx, and you integrate it. So that will give the Fourier transform for the given function. So we have simply just combined these two cos and sine both together by plugging in the coefficients of a and b, and then you write down the combined formula, and then you add the sinusoidal term by applying the Euler's formula. You should get the whole integral in the exponent form. Okay, so that will be your Fourier transform. So let us do some example, so that should give us more clarification. So if you take the first example, f of x, maybe a simple one, that f of x equal to 1 for moduli x less than 1 and is equal to 0 otherwise. So you have to find out the Fourier transform of this function, f of x equal to 1 moduli x less than 1 and is equal to 0 otherwise. So simply you just write down the equation 1 over under root 2 pi integral from minus infinity to plus infinity. Now this is, we have only the moduli x less than 1, so this is nothing but minus x less than 1. So you have only the integral between minus 1 to 1. Rest of the values for which the function is 0, so you don't consider that. So 1 into e to the minus I wx dx. Okay, so it's a very simple integral. It's a very simple integral one can do. So this should be equal to 1 over under root 2 pi e raised to minus Iwx over minus Iw integral minus 1 to 1. Okay, so if you just simplify this, you should get I over under root, this is minus 1 upon I, so I'm writing it over here, I over under 2 pi, and you should get this e pi over e to the power minus Iw minus e to the power minus Iw. So that is nothing but minus 2y times sine w. ठीक है, इसको मैंने I have just written it directly. So this should be equal to under root 2 over pi sine of w over w. ठीक है, so that is going to be your Fourier transform. So similarly, let's take one more example, and then we'll just define in brief the Dft and Fft. What is Dft and Fft? So Fourier transform of e to the power ax, f of x equal to e to the power minus ax for x greater than 0, and for x less than 0, the function is going to be 0 and a is positive. So for this function, if you find the Fourier transform, and simply you take the integral minus infinity to plus infinity, but you have only 0 to infinity, so you should have 0 to infinity, because otherwise the function is 0. So e raised to minus ax into e raised to minus Iwx dx. Okay, so this is something very simple integral, so I would just expect you to do it. So So this is going to be equal to 1 over under root 2 pi over 1 a plus I w. So you should get this answer. Okay, so let's just I will give you some examples that you do it in your assignment. So so you have the example of e to the power 2ix 2ix for modulus of x less than 1 and equal to 0 otherwise. Second example, f of x equal to x into e raised to minus x to minus 1 less than x less than 0 and is equal to 0 otherwise. That's the second one. And the third one, f of x equal to minus 1 less than x less than 0 and is equal to 1 0 less than x less than 1 and is equal to 0 otherwise. Okay, so these three examples you should be doing in the assignment. Find the Fourier transform. Find the Fourier transform. That's the question. Okay. Okay, so let us just summarize this and we just come to the DFT and FFT. So DFT and FFT is simply nothing but a sort of a theoretical aspect of your Fourier transform. Okay, so what exactly we have done is that we obtain this Fourier transform, which we denoted by f hat, and this is nothing but actually it is the intensity of the function. It is the intensity of the function f of the function in the interval between w and w plus delta w. I mean, if you talk of in terms of the signal analysis context, if you talk about this in the context of signal analysis, then this is it is nothing but the intensity of your function in the interval between w and w plus delta w, or I mean it is for a very small interval delta w, and this actually interprets the spectral density. If you talk about let's say optics phenomena, in terms of optics phenomena, so this would indicate the spectral density of the signal. And we know from I mean, even in quantum mechanics you might have gone through this, that if you take up the integral of such functions and if you take the complex conjugate and if you take the f hat moduli square over the element dw, then this should give you the probability. I mean, this gives you the probability for the given spectral density, and if you multiply it by the volume, or I mean that the element over which you are taking the integral, then this should give you it is associated with the total energy of the system. Total energy of the system. Okay, this whole integral. And we know from theory that energy is generally proportional to the amplitude square. I mean, in terms of the wave analysis, that energy is proportional to the amplitude square. And if your system has some periodic solution, like we see in the Fourier series, and if your system has a periodic solution, like the way we have in the Fourier series, Fourier series में जैसे होता है, I mean, we see the terms in term A1, A2, A3, A4, B1, B2, B3, like that in the segments. So if the system has a periodic solution in the form of a Fourier series, then each energy spectrum will have a multiple squares of amplitude. Each energy spectrum will have a multiple squares of amplitude. Okay. And so that if you combine all of this, then we actually call it discrete spectrum. We call it as a discrete spectrum. So what we are saying is that if the given physical system has a solution which is a periodic in nature, like the way we have it in the Fourier series, then for each frequency you will have a multiple amplitude square, and you will have a multiple amplitude square, and that we refer to as a discrete spectrum for the given signal. And when you apply the Fourier transform to such discrete spectrum, so that is what we call the discrete Fourier transform, DFT. Okay, that is what we call discrete Fourier transform. And generally, if we do it mathematically, I mean, with pen and paper, if you do the signal analysis, then this discrete Fourier transform actually takes two long calculations. And like if you have some thousands of samples you have, and if you perform for each sample having a discrete frequency, having a frequency spectrum, and each spectrum has a multiple amplitude square, and for each amplitude you are performing the Fourier transform. So this actually becomes a very lengthy process, or I mean, it's very difficult to do it with just by pen and paper. So that's why we develop this sort of computational tools. So one of such technique to actually perform this DFT is actually called fast Fourier transform. So DFT, when you actually write down the algorithm for such discrete Fourier transform for a given sequence, then this will give you the whole range of new complete transformation. So that would call the fast Fourier transform. Okay. And these things are generally done in your computer software. So maybe you can do it on MATLAB, or there are so many different softwares. Python is there, Maple is there, Mathematica is there. So there are plenty of such softwares. So one can perform these all operations in those softwares, and you can obtain the Fourier transform very easily. And because of course we cannot go and do the Fourier transform for each discrete spectrum, because in reality, if we talk about these signals, so generally we obtain the solution in these intervals, and it has a discrete spectrum, especially if you take any quantum mechanical system. And for those particular systems, when you analyze the data, so you will have the discrete spectrum, and you need to apply the Fourier transform for that. And if that discrete spectrum has to be performed over large number of samples, then that is called fast Fourier transform. So fast Fourier transform is nothing but it is an algorithm which computes the DFT for the given sequence. Now, it is the algorithm written for the given sequence for the given DFT. So that is called fast Fourier transform. So that one can do in the software. So I'm not sure if in your computational lab this is there in your syllabus or not, but you can try it on your own with your laboratory course. ठीक है, computational course में शायद I think हो सकता है उसमें. So that is all about discrete Fourier transform and fast Fourier transform. Now, so far what we have done is simply what mathematically we came up to this formula of the Fourier transform. Yeah, this one. So whatever we have done so far is simply a mathematical, we have come up to this formula. Now, one can get an intuitive idea how this Fourier transform is useful in analyzing the signal. And one can get an intuitive idea by understanding it with a small steps in, what is the physical interpretation of this whole Fourier transform. So for that I would like to see a video. Okay, so we'll watch one video and it should give us to some more clear picture.
This right here is what we're going to build through this video. A certain animated approach to thinking about a super important idea for Fourier. For anyone unfamiliar with what that is, my number one goal here is just for the video to be an introduction to that. But even for those of you who are already familiar with it, I still think that there's something fun, which is about seeing what all of this actually is. The simple example to start is going to be the classical.
So if you see this particular example, so it is simply that you have one signal which is having a multiple frequencies, and when you want to identify which frequencies this signal is made up of, then you can take up the Fourier transform of this signal, and these all waves, when you join together, then it gives you this spectrum. So if you want to decompose the signal, then we apply the Fourier transform.
But after that, how do you how this idea extends well beyond sound to then seemingly ways for it to happen? Good. It is crazy just how ubiquitous this is. Let's dive in. This sound right here is a pure hit, 440 beats per second. Meaning, if you measure the air pressure right next to your headphones, your speaker, as a function of time, it would oscillate up and down around its usual equilibrium in this way, making 440 oscillations each second. A lower pitch note is the same structure, just 4 beats per second. When both of them are played at once, what do you think the resultant pressure versus time graph is? Well, at any point in time, this pressure difference is going to be the sum of what it would be for each of those notes individually. Which, let's face it, is kind of a complicated thing to think. At some points, the beats match up with each other, resulting in a really high pressure. At other points, they tend to cancel out. And all in all, what you get is a wave-ish pressure versus time graph that is not a pure sine graph. It's something more complicated. And as you add in other notes, the wave gets more and more complicated. Right now, all it is a combination of 4 frequencies. It seems needlessly complicated given the low amount of information put in. A microphone recording any sound just picks up on the air pressure at many different points in time. It only sees the final sound. So our simple question is going to be how you can take a signal like this and decompose it into the 4 frequencies that we've done. Pretty interesting, right? Looking at those signals really mixes them all together. So pulling them back apart feels akin to unmixing multiple colors that have all been stirred up together. The general strategy is going to be to build for ourselves a mathematical machine that treats signals with a given frequency, how it treats others. To start, consider simply taking a pure signal, say with a low 3 beats per second, so that we can plot it easily. And let's limit ourselves to looking at a final portion of this graph, in this case, the push between 0 seconds and 4.5 seconds. The key idea is going to be to take this graph and sort of wrap it up around the circle. Concretely, here's what I mean by that. Imagine a little rotating vector where at each point in time, its length is equal to the height of our graph for that time. So high points of the graph correspond to a greater distance from the origin, and low points end up closer to the origin. Right now, I'm drawing it in such a way that moving forward 2 seconds at a time corresponds to a single rotation around the circle. Our little vector drops around that graph. So this is important. There are two different frequencies at play here. There's the frequency of our signal, which goes up and down 2 times per second. And then, separately, there's the frequency with which we're wrapping the graph around the circle, which at the moment is half of the rotation per second. But we can adjust that second frequency however we want. We want to wrap it around faster, or maybe we go and wrap it around slower. And that choice of winding frequency determines what the round-up graph looks like. The diagrams that come out of this can be pretty complicated, although they are very pretty. But it's important to keep in mind that all the happening is that we're wrapping the signal around the circle. The vertical lines that I'm drawing on top, by the way, are just a way to keep track of the distance on the original graph that corresponds to a full rotation around the circle. So lines spaced out by 1.5 seconds, the unit takes 1.5 seconds to move one full revolution. And at this point, we might have some sort of vague sense that something special will happen when the winding frequency matches the frequency of our signal, 3 beats per second. All of the high points in the graph happen on the right side of the circle, and all of the low points happen on the left. But how precisely can we take advantage of that in our attempt to build a frequency unmixed machine? Well, imagine this graph is having some kind of mass to it, like a metal wire. This little dot is going to represent the center of mass of that wire. As we change the frequency and the graph lines up with it, that center of mass kind of wobbles around a bit. And for most of the winding frequency, the peaks and the valleys are all spaced out around the circle in such a way that the center of mass stays pretty close to the origin. But when the winding frequency is the same as the frequency of our signal, all of the peaks are on the right, all of the valleys are on the left, so the center of mass is unusually far to the right. Here, to capture this, let's draw some kind of plot that keeps track of where that center of mass is for each winding frequency. Of course, the center of mass is a two-dimensional thing. There's 2 coordinates to follow 2 track of, but for the moment, let's only keep track of the coordinates. So for a frequency of 0, when everything is bunched up on the right, this x coordinate is relatively high. And then as you increase that winding frequency, and the graph balances out around the circle, the x coordinate of that center of mass goes closer to 0. It just kind of wobbles around. Then, at 3 beats per second, there's a spike, as everything lines up to the right. This right here is the simple function. Let's sum up what we have so far. We have that original intensity versus time graph. Then we have the round up version of that, some two-dimensional. And as a third thing, we have a plot that has a rounding frequency that influences the center of mass of that graph. And by the way, let's look back at those really low frequencies near 0. This big spike around 0 in our new frequency plot, this corresponds to the fact that the whole cosine wave is shifted up. If I had chosen a signal that oscillates around 0, dipping into negative values, then as we play around with various frequencies, this plot of the winding would only have a spike at the value. But negative values are a little bit weird and messy to think about, especially for our first example. So let's just continue thinking in terms of shifted up. I just want you to understand that that spike around 0 only corresponds to the shift. Our main focus, as far as frequency decomposition is concerned, is that dot. full plot is what I call the almost Fourier transform of the original signal. There's a couple of small distinctions between this and the actual Fourier transform, which I'll get to in a couple of minutes. But already, you might be able to see how this machine lets us pick out the frequency of the signal. Just to play around with it a little bit more, take a different pure signal, let's say with a lower frequency, and do the same thing. Wind it around the circle. Imagine different potential winding frequencies. As you do that, keep track of where the center of mass of that graph is. And then plot the x-coordinate of that center of mass as you adjust the winding frequency. Just like before, we get a spike when the winding frequency is the same as the signal. This basically equals 2 cycles per second. But the thing that makes this machine so delightful is how it enables us to take a signal consisting of multiple frequencies and pick out what they are. Imagine taking the two signals we just looked at, the wave with 3 beats per second and the wave with 2 beats per second, and add them. Like I said earlier, we no longer a nice pure cosine wave. It's something a little more complicated. But imagine throwing this into our winding frequency machine. It is certainly the case that as you wrap this thing around, it looks a lot more complicated. Chaos, and then whoop, things seem to line up pretty nicely at 2 cycles per second. And as you continue on, chaos, whoop, things nicely align again at 3 cycles per second. Like I said, the round-up graph can look kind of busy and complicated, but all it is the relatively simple idea of racking and racking.
So what we have been watching so far is that if you take up this any curve and you wind up in a circular plot, and when you wrap up those graph, and if you track the x coordinate of the center of mass, then what we are finding is that it exactly when your winding frequency matches with your original frequency, you get a peak over there. Like in this case, 2 hertz and 3 hertz. So that is how one can decompose these signals. Okay. So we will now next just move on to how mathematically this has to do with the exponential of IWX. I mean the power that we had chosen, e to the power I into WX. So that we will see next.
It's the same as if you first added up the signal. You could test to verify for yourself that it's clear what exactly is being measured inside this winding machine. Now, this property makes things really useful to us because the transform of a pure frequency is close to 0 everywhere, except for a spike around that frequency. So when you add together two pure frequencies, the transform graph just has these little peaks above the frequencies that you need. So this little mathematical machine does exactly what we want. It pulls out the original frequencies from their jumbled up sounds, unmixing the mixed content. But before we get into the full math that describes this operation, let's just get a quick glimpse of one context where this thing is useful. Sound editing. Let's say that you have some recording and it's got an annoying high pitch that you would like to filter. Well, first, your signal is coming from a function of various intensities over time. Different voltages given to your speaker for 1 millisecond. But we want to think of this in terms of frequency. So when you take the Fourier transform of that signal, the annoying high pitch is going to show up just as a spike at some high frequency. Filtering that out by just pushing this button down, what we'll be looking at is the Fourier transform of a sound that's just like your recording, only without that high frequency. Luckily, there's a notion of an inverse Fourier. It tells you which signal would have produced this as its Fourier. I'll be talking about that inverse much more fully in the next video, but long story short, applying the Fourier transform to the Fourier transform gives you back something close to the original function. Kind of. This is a little bit of a lie, but in the direction. Most of the reason that it's a lie is that I still have yet to tell you what the actual Fourier transform is, since it's a little more complex than this obscure simple concept. First off, bringing back this round-up graph, the x-coordinate is really only half the story, right? This thing is got a wide portion as well. And as is typical in math, whenever you're dealing with something two-dimensional, it's elegant to think of it as the complex graph, where this center of mass is going to be a complex number. It has both the real and the imaginary. And the reason for talking in terms of complex numbers rather than just saying it has two coordinates is that complex numbers lend themselves to really nice descriptions of things that have to do with one location. For example, Euler's formula famously tells us that if you take e to some number times I, it will land on the point here if you were to walk that number of units around the circle with radius counterclockwise starting on the right. So, imagine you wanted to describe rotating at a rate of 1 cycle per second. And then you take the expression e to the 2 pi times I times t, where t is the amount of time it has. Since for a circle of radius 1, 2 pi describes the full length of its circumference. And this is a little bit dizzying to look at, so maybe you want to describe a different frequency, lower. For that, you would just multiply that time t in the exponent by the frequency, f. For example, if f was 1/10, then this vector makes 1 full turn every 10 seconds, since the time t has to increase all the way to 10 before the full exponent is like 2 pi I. I have another video giving some intuition on why this is the behavior of. But for right now, we're just going to take it as a given. Now, why make a well, it gives us these really nice ways to write down the idea of landing a graph into a single calculator form. First off, the convention in the context of Fourier transforms is to think about rotating in the clockwise direction. So let's go ahead and throw a negative sign for that up. Take some function describing a signal intensity versus time, like this pure cosine right behind it. Call it g of t. If you multiply this exponential expression times g of t, it means that the rotating complex number is getting scaled up and down according to the value of this function. So you can think of this little rotating vector as changing height as drawing your line of graph. So think about it. This is awesome. This really small expression is a super elegant way to encapsulate the whole idea of winding a graph around a circle with a variable frequency. And remember, the thing we want to do with this round-up graph is to track its center of mass. So think about what formula is going to capture that. Well, to approximate it, we might sample a whole bunch of times from the original signal, see where those points end up on the round-up graph, and then just take an average. That is, add them all together as complex numbers, and then divide by the number of samples. This will become more accurate if you sample more points, which are closer together. And in the limit, rather than looking at the sum of a whole bunch of points divided by the number of points, you take an integral of this function divided by the size of the time interval. Now, the idea of integrating a complex value function might seem weird, and this should be with calculus, maybe even but the underlying meaning here really doesn't require any calculus. The whole expression is just the center of mass of the round-up graph. So, great, step by step, we have built up this kind of complicated, but let's face it, surprisingly small expression for the whole winding machine field at a time. And now there is only one final distinction to make out between this and the actual unforgiveness Fourier. Namely, just don't divide out by time. Fourier transform is just the integral part. What that means is that instead of looking at the center of mass, you would scale it up by some amount. If the portion of the original graph you were using spanned 3 seconds, you would multiply the center of mass by 3. If it was spanning 6 seconds, you would multiply the center of mass by 6. Physically, this has the effect that when a certain frequency persists for a long time, the magnitude of the Fourier transform at that frequency is scaled up more and more.
Yeah, I think this should be good enough to watch for the moment because it has some more thing to go on. I'll put the links in the description of our Teams group, so you can watch the whole video. But the whole idea is to just see how this expression that we were talking about in our mathematical derivations is connected in reality with decomposing phenomena. So as we said that it is mostly used for the decomposition of the frequency signals, and how this exponential term, when multiplied by the given function, it actually appears to be winding around the given circle And by keeping the track on the center of mass, one can actually find out at which frequency and how many signals are combined in the given particular function that you are assigned to. Okay, so I think that is it. We should end up over here. I will put up this link in the description, and you can go for more if you want to see this particular video. And this would end over here, our Fourier transform unit completely. Notes I have already given to you, so you can follow those notes, and the assignments that I have been given to you. So just follow those assignments and put it up in your assignment notebook. Okay, if you have any questions, you can ask. Otherwise, we'll just end up over here. Okay, so if you don't have any questions, then we'll end up over here. Thank you. Thanks for your attention and have a good day. Bye.
Thank you, sir.